Welcome to this explainer. Today we're looking at a machine so unbelievably advanced, it can actually print features smaller than a single virus. We're talking about extreme ultraviolet lithography, or EUV. It is an absolute engineering marvel. Literally, it's the invisible force powering the modern world. Without it, no AI breakthroughs, no high-end GPUs, and definitely no ultra-fast smartphones sitting in your pocket right now.
Okay, let's dive into this. Here is our roadmap. First up, the microchip bottleneck. Then, creating extreme ultraviolet light. After that, mirrors in a vacuum, printing the perfect chip, and finally we'll wrap up with the future of innovation.
To really wrap our heads around what we're dealing with here, we have to talk scale. This isn't just some standard piece of factory equipment. We're talking about a single machine that costs over $350 million to build.
And the crazy part? Even though its whole job is to create microscopic, nanometer-scale output, the physical footprint required to actually pull that off is absolutely massive. One of these units weighs in at nearly 180 tons.
Inside that massive 180-ton frame, the complexity is just staggering. We're looking at more than 100,000 precision components, and they all have to work together with literal atomic-scale accuracy. It's basically a symphony of extreme engineering.
Section 1. The microchip bottleneck. So, what exactly is lithography? Well, think of it like using a stencil and ink to paint a design on a t-shirt. But in this case, our ink is actually light, and our paper is a highly polished silicon wafer. Basically, the smaller the wavelength of that light, the tinier the circuits you can print. And tinier circuits mean way more transistors and vastly better performance.
So, the crucial point is this. For decades, chipmakers relied on deep ultraviolet, or DUV, light, which has a 193 nanometer wavelength. But trying to make today's impossibly tiny chips with that older, kind of fatter light requires crazy complex, time-consuming multiple patterning steps. Extreme ultraviolet, or EUV light, completely changes the game. It operates at a ridiculously small 13.5 nanometers. That ultra-short wavelength lets us print unbelievably intricate patterns directly onto the silicon in far fewer steps.
Section 2. Creating extreme ultraviolet light.
Okay, the process of actually generating this 13.5 nanometer light is straight-up science fiction playing out in real time. First, the machine releases microscopic droplets of molten tin, each one just 25 micrometers across. As it falls, a high-powered carbon dioxide laser fires a pulse just to flatten the droplet out. Then, a split second later, a second massive laser pulse fires, blasting that flattened tin and completely vaporizing it into plasma. Now, it's a highly inefficient process. Only a tiny fraction of the laser's energy actually becomes useful light, but it is absolutely essential to get that EUV radiation.
And get this, when that second laser hits, the resulting plasma reaches a mind-boggling 200,000 degrees Celsius. To put that into perspective, that is literally many times hotter than the surface of our sun, all happening inside a machine here on Earth. And it's from that intense contained plasma burst that our precious 13.5 nanometer EUV light is finally born.
Section 3. Mirrors in a vacuum.
Let's slow down for a second, because making the light is really only half the battle. We also have to control it. And here's the massive complication we face. Normal glass, or even quartz, completely absorbs EUV light instantly. Traditional lenses? Entirely useless. Worse yet, if this extreme light touches just normal everyday air, it disappears. It gets completely absorbed before it can ever reach the silicon.
Now, what's really interesting about this slide is how engineers brilliantly solved this seemingly impossible problem. First, they completely eliminated the air. The entire optical path has to operate inside an ultra-high vacuum chamber. Second, instead of glass lenses, they use highly specialized multi-layer mirrors. We're talking about roughly 40 alternating layers of molybdenum and silicon, with each layer being only a few nanometers thick. But here's the kicker. Even with all that crazy precision engineering, each mirror still only reflects about 70% of the incoming EUV light. And since the system needs multiple mirrors to bounce and guide the beam, only a tiny fraction of the original light actually makes it to the wafer.
Section 4. Printing the perfect chip.
So, how do we actually get the pattern onto the chip? Well, that hard-won EUV beam is carefully bounced through all those precision mirrors. It then strikes a reflective photomask, which is basically the ultra-detailed blueprint for our chip, and projects that image onto a silicon wafer coated with a special chemical called photoresist. After that, the exposed photoresist undergoes chemical development. The unwanted material gets etched away, and new materials are deposited. And to build a modern processor, this incredibly delicate, precise process repeats, layer by layer over 100 times.
Doing all of this at a microscopic scale introduces some brutally difficult engineering challenges. You have ultra-precise mirror alignment. You have to maintain nanometer-level vibration control inside a massive industrial facility. You've got to hold that ultra-high vacuum, manage the tin particle contamination from our little plasma mini-suns, and keep every single optical layer perfectly clean. Coordinating thousands of moving components with atomic-scale accuracy means each one of these systems takes literally months to assemble and test.
So, why does all this extreme engineering actually matter to you and me? Think about the smartphone in your hand, or the AI accelerators driving huge tech breakthroughs, the high-end graphics cards in your computer, or even the advanced processors inside modern cars. Nearly every high-end device we use today runs on advanced 7nm, 5nm, or 3nm chips, and absolutely none of them would exist today without EUV technology, for sure.
Section 5. The Future of Innovation.
Let's move to and see how this builds into the future. The next massive evolution is high numerical aperture, or High-NA EUV. It basically uses a larger numerical aperture to capture a wider range of light angles, which gives us even higher resolution. This is the exact technology that's going to allow humanity to draw even smaller transistors, finally breaking the 2nm barrier, all while using fewer processing steps and delivering way better image quality.
When you step back and look at it, extreme ultraviolet lithography represents one of humanity's greatest engineering achievements. This isn't just a manufacturing tool, it's a monumental triumph of human ingenuity. We have somehow figured out how to harness vaporized tin plasma, ultra-high vacuums, and nanometer-perfect optics to quite literally build the modern world at an atomic scale. Which leaves us with one incredibly thrilling question. With High-NA EUV unlocking the 2nm barrier and beyond, what are we going to build next? Just imagine the future of artificial intelligence, or quantum computing, all built on these impossibly small, impossibly perfect foundations. Thanks so much for joining me for this explainer.